All right, so what we know, um, at some point in our careers, we learned about sequences and series. It might have been in pre-calculus, it might have been in Calc 2, but at some point, hopefully that language was familiar to us.
Mhm.
Maybe again, even in discrete, comes up in discrete quite a bit. You're looking for those different patterns. But in particular, in this class, we've also looked at linear, homogeneous, second order differential equations, and specifically looking at ones that have non-constant coefficients. And so with the non-constant coefficients, that means we can't use the idea of characteristic equations to solve that. In fact, we have to come up with some other methods. And some of those other methods have involved guessing a solution of a form and then kind of seeing where that goes. And so this is what we're going to learn now is sort of like a different approach to solving these differential equations with non-constant coefficients, right? That's really what we're going to look at next week. So, so this will be like 6.2 and 6.3, right? Now, what's new today, it's not necessarily new content, but we are looking at what I like to call the salient features or the important features of the power series. And I don't know how your experience was with sequences and series, but I remember walking out of Calc 2 when I took it many, many years ago, being like, I hated it at the time. Like I didn't understand what we were doing. And it was really, I think, one of the first times that I had been asked to like make decisions about what might work best here, what might work best there, how do we know? And I feel like I got really tripped up in the language. And so it is something that I really like to take the time to make sure that we understand, especially as we move into next week with our series solutions. All right. So let's kind of start a little bit at the beginning. Once upon a time, we learned something about sequences and series. And they often get said together, but I just want to make sure that we know the difference between the two. Okay. And so, most simply, a sequence we can define as a list of numbers that follow a pattern. All right. So, a list of numbers that follow a pattern. And so, for example, we could say something like 1, 1, 2, 3, 5, 8. That would be considered a sequence, right? And in particular, this one is the Fibonacci sequence. But we can take those list of numbers, we can identify the pattern that goes with that. There are explicit equations, there are recursive equations. There's a lot of different kinds of equations for them, but ultimately a sequence is just something that is a list of numbers that follow a pattern. Now we're going to be working on series. All right. So the only difference between a sequence and a series is this one word. It is the sum of the numbers in a list that follow a given pattern. Right? So it is the sum of the numbers in a list that follow a given pattern. And so if we were to take a look at the Fibonacci sequence that we just looked at, we wouldn't say like 1, 1, 2, 3, 5, 8, but rather we would say 1 plus 1 plus 2 plus 3 plus 5 plus 8. And we would keep going. Right? And that is genuinely the difference between a sequence and a series, which when I discovered this after taking Calc 2, I was like, oh, that makes so much more sense. But basically, we're taking those commas and we're turning them into addition signs. And with our series, we can have two kinds of sums. We can have a partial sum, right? Or sometimes we can have an infinite sum. And partial sum is just saying, I want to take some of the numbers, like the first three, and I want to add them together. And so a partial sum of this particular series might be 4, or it might be 8, or it might be 16, right? So we can sort of add certain clusters of these numbers together and get a partial sum. The infinite sum is like if I took all of the numbers in the entire sequence from the first term to the second term, third term, all the way to the infinite, like the very, very last term in this series, and I added them all together, if I could get a number, that would be considered an infinite sum. Okay. Now, using your intuition here, or maybe your previous knowledge, do we think that 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus, and we get an infinite sum, do we think that is going to approach a number value? Yeah, and I would agree that we're not going to get a numerical value because we're just going to keep adding bigger and bigger numbers, and so it's going to end up being infinite. Okay, but there are some series out there where if you add the numbers and you keep adding and you add every single number in the entire series, that it actually does get to a single value. Okay, and so that idea is really what we mean when we talk about converging versus diverging, right? Now, again, depending on your Calc 2 experience, you may understand convergence and divergence very well, or you may be like, I was one of the two words that I was guessing anytime I saw a problem. That if the question said, is this converging or diverging? You just kind of guessed one of them and you're like, it's diverging. I don't know why, but I used converging last time, so I'm just going to write diverging now. But I think as we move forward, it's going to be really important that we know how to determine whether something converges or not. And so let's get a little bit more of a definition about what converging and diverging means, right? So if we are looking at a sequence here, okay, a sequence converges when the list, no, when the numbers in the list approach a numerical value as we get to the, I'm going to put this in quotes, to the end of the sequence. All right, so in a sequence converges when the numbers in the list approach a numerical value as we get to the end of the sequence. And so another way of saying that is as we get to infinity, all right, we're looking at like the very last term in this sequence, are they sort of plateauing and getting close to a given number? And so if we think about that graphically, I think sometimes looking at a picture is really helpful. So if any of you are looking to take analysis at some point in your career, which is typically like a 300 level class, I think mostly for pure math majors. I don't know if applied math majors have to take it, but I would encourage you to draw a lot of pictures. So if you're thinking about when a sequence converges, if you draw just like a XY coordinate, and you were to think about all the terms in your sequence, maybe you have one that's like this term, this term, this term, this term, this term, this term. And as you keep going out to infinity, your graph, so to speak, starts to level out. And once upon a time, we called this leveling out a horizontal asymptote. But it turns out that when we say, what does the sequence converge to? if you plot sort of the corresponding graph of the sequence, and if it has the horizontal asymptote, that is your convergence value. Right, so when we talk about sequences and series, there's actually a very visual dimension that we can add to this. And I know that I'm a very visual learner, so that sort of makes more sense to me. But series are a little bit different when we talk about convergence or divergence. So when the sum of the numbers in the list approach a numerical value, as we get to the end of the series, okay? And so maybe a good idea about that is something like this. So let's say we had 1, and then we cut that in half, and then we cut it in half again, and we cut it in half again, and we cut it in half again, and you keep cutting things in half. Right. This is something that maybe you remember called a geometric series, right? We are losing 50% every single time. And it turns out that this series converges because as I get towards the end, I'm going to be adding just like the tiniest bit of a number, like 1/2 to the n, like a really, really small number. And so at some point, even though I continue to add numbers, those numbers are so small that we can say that the sum of the entire series actually gets to a numerical value. And that would mean that that series converges. Okay, so that's a good question to kind of frame it. Like if we add all of the terms in here, does that sum keep getting bigger? That would be diverging. Or does that sum sort of get to a specific value? All right, meaning that what we keep adding gets closer and closer to 0. So we're not really changing the value of that infinite series. Okay. So that's what we mean when we're talking about convergence. And divergence, we can almost just say, is going to be the opposite. So when these things are not fulfilled, okay? So a sequence diverges when the numbers in the list approach positive infinity or negative infinity, or they oscillate. Okay, so you might imagine a situation where you have your points on your series, they just keep going up and up, which means every time you are adding something, you're adding a bigger and bigger and bigger number. So when you add them all together, you're going to get to positive infinity. But on the flip side, if you keep on adding more negative numbers, you would be getting closer to negative infinity. But there's actually this sort of exception to this where we might end up sort of oscillating. And so maybe something where you're getting positive and negative values, but they don't necessarily all cancel each other out. Okay. And series, sort of similar idea that if we don't get to a number, like a numerical value, as we keep adding, if we get to positive or negative infinity, then that means that we are going to have a divergent series. All right. So keep that in mind as we kind of move along, that like sequences and series, convergence and divergence is really the underpinnings of what we're talking about here. All right, so what about the power series? All right, you learned a lot about a lot of different kinds of series, like there's the harmonic series, the P series, lots of different kinds of series, but one of the most powerful ones in mathematics is something called the power series. And the power series is basically a function that can be expanded to be in the following pattern, okay? So maybe we start over here, okay? We have a first term. So a sub 0 is a number for us right now, okay? Then we have a sub 1 x minus x sub 0. And we might notice here that the power is actually a 1. The second term, or the third term rather, a sub 2 x minus x 0 squared. So notice that this 2 and this squared are the same value. And as we keep going, we might be able to generalize the term to say a sub n x minus x naught to the n power. And you'll notice that we are adding all of these terms together. And so we know that we have a series because we are adding things together. And so our more functional way of writing that, we have our sigma notation, all right? So sigma meaning we're going to add. Well, what are we going to add? We're going to take this equation or this expression that we have here, and we're going to start plugging in numbers for n. We're going to plug in 0, we're going to plug in 1, we're going to plug in 2, 3, 4, and we're going to keep plugging in until we get to the end. We get to infinity, all right? And if we add these all up, we will get our power series, all right? Now, different books use different notations. I think in your book, in our book, this a sub n, I think they use a C, all right? And I think they use the A over here. So that might be a little confusing, but it's more important to think about where the location of a letter is rather than what the actual letter is. But what we have above is something we could call a power series centered at x equals x sub 0, okay? Now, where something is centered is actually going to be important in our conversation. But before we get there, let's talk about some notation, all right? So I did want to start with like an actual example right here. And so if we were to say 1 plus 2x plus 4x squared plus 8x cubed, and we wanted to write it in sort of this notation, in the sigma notation, we might say that this is a sum of n from n equals 0 to infinity. And how would we express this? Like, what would my a sub n be? Like, what function could we use to define that a sub n? So if I look at my coefficients, I've got a 1, a 2, a 4, an 8. I bet that next coefficient is going to be a 16 and then a 32. So maybe it seems like we're looking at powers of 2, and we want to tie it back to like n. So we don't want to just write like powers of 2, but we could say 2 to the power of n, all right? And let's just double check this. 2 to the 0 gives me 1. 2 to the 1 gives me 2. 2 to the 2 gives me 4. 2 to the 3 gives me 8, right? So I can define that starting term by just saying 2 to the n. And as far as the part that depends on the x goes, it looks like we have x minus 0 to the n, right? Now, not everyone is going to write a 0 here, and that's okay. Some people might write it something like this, all right? But how we would describe this middle one is this is a power series centered at x equals 0, okay? Now, one of the things that is actually useful a lot in differential equations is sometimes we actually want to see sort of that first term by itself, and then we write a sum of all the other ones. So in other words, we sort of strip out the first term, right? So occasionally you might have a power series written like this. So instead of saying starting at 0 and having your power series, you would write it as a sub 0. So that's taking out the first term plus the rest of it. Now this part stays the same, but how do I change this part to say now I only want to start at the first term, or at a sub 1, not at a sub 0? I can make one small change in the notation to do that. And so this will be something that we sort of uh, take a look at more deeply at the end. But it turns out like we're still going to be adding all the terms as we get to infinity, right? But this first, the bottom value says n equals 0. That means like I'm starting by plugging in 0. But if I've taken that away, then down here, I don't want to write n equals 0, but rather I want to say n equals 1. So I'm starting at the second term now, okay? So you'll have your starting one and then plus the rest of it. And that is, again, very common to see in differential equations. Now, this next question is more just like an extension, a check for understanding. We could strip out as many terms as we want, right? It doesn't have to be just the first one. And so I'm wondering if you could tell me, how might we modify this if I wanted to have the first 4 terms and then the rest of it? What might that look like? Well, if we're not sure, I think one of the best ways to approach this is write out a few terms and then see what happens, okay? And so in particular, we're going to write out the first 4 terms. So we have our first term, a sub 0, our second term, a sub 1, x minus x naught, the third term, a2, x minus x naught squared, the fourth term, a sub 3, x minus x naught cubed, plus, now I can say the rest of it all together. The top will be infinity because I'm still going to the end. Perfect. But that bottom number is now going to be 4. All right. So we want to make sure that we understand how this bottom number tells us about what we're going to be, like where we're going to be starting. Because at the very end of this lesson, we'll talk about something called index shift, all right? Shift, S-H-I-F-T. We'll talk about an index shift, and that'll be a skill that we use a lot next week in 6.2, okay? So part of what we're doing right here is just kind of getting comfortable with the notation so that we can use it later next week. Now, one thing to keep in mind is that I apparently didn't get the screenshot to save. But one thing to keep in mind is the convergence like, why is convergence important, right? So we started our lesson talking about sequence versus series, and then convergence versus divergence. And, no matter what memories that sort of brought up for you in terms of, looking back at Calc 2, convergence is actually really important to what we're going to be talking about next week. Because, excuse me, for a given power series, we're going to have some non-negative number, okay? And so we might say that this number, non-negative, we can say that it could be 0. We typically use rho, right? So I'm going to erase that and draw it again because it looks like a P if you're not too careful, right? So the Greek letter rho, or sometimes we use R, lowercase r, for the radius of convergence, but this rho has to be between 0 and infinity, right? Now this radius of convergence, so rho is the Greek r, right? So radius of convergence, that number is so important because it tells us whether a power series will converge and when it will diverge, right? So we want to make sure we know, when is this going to converge? When is this going to diverge? And so at some point next week, it might be very important for us to look into that a little bit more deeply, all right? But in particular, we can say that a power series will converge when this goes back to our x minus x naught that we saw in all of the terms. So when x minus x naught, okay, and we're going to put that in absolute values because we just defined rho to be a non-negative number, right? So we want to make sure this value is positive. But if the difference between x minus x naught is less than rho, we're going to have a convergent power series. Whereas it will diverge when x minus x naught is greater than rho. All right. So let me see if I can rescue what I had intended on having here. All right. So one of the most common tests that perhaps you learned in Calc 2, looking at convergence and divergence, especially around like a power series, is something called the ratio test. All right, so I hope that sounds familiar to folks. But the ratio test is one of the, I don't want to say easy, that sounds so disheartening if it wasn't easy for you, but it is one of the most straightforward ways that we can figure out whether something converges or diverges, okay? And so in particular, we're going to say that our limit, all right, if we find the ratio, so we're going to take a limit as n approaches infinity of the ratio of two terms. So like the one term, so a sub n minus 1, or n plus 1, over the term before it, a sub n. So we take that ratio. And in addition to that, we're going to use this idea of the radius of convergence, like wanting that to be less than a certain value. If we multiply that by our x minus x naught, like whatever our center point is, right? Then the result will be one of three values. And these three values will tell us whether or not that series converges or diverges, right? So if we get L is less than 1, we have convergence, right? If you have L is less than 1, you're going to get convergence. If you have L is greater than 1, you're going to have something diverge, okay? The one drawback to this test, what happens if L equals 0? It's a toss-up. We don't know. We would have to try a different test. All right. So for this pink one in the middle, I'm imagining that shrug emoji where it's like, I don't know, right? It could be either one. This test was actually not useful in that case. But when we're looking at most series and a specific set of numbers that are moving in a certain way, typically we will be able to find that either it's less than one or it's greater than one, right? But the main focus of today, like all of this is kind of like background knowledge, a little bit of concept stuff. But the main part of what I want us to take out today is like, what computation should we sort of start to have on our radar? So when they pop up in the middle of a really long problem next week, that we're able to draw upon this, okay? And so let us begin talking about some manipulation techniques. And by manipulation, there's sort of four main categories I want to describe. We're talking about addition and subtraction. We're talking about multiplication. We're talking about differentiation, which is a fancy word of saying taking derivatives. Right. And then we'll get to that one that I said is going to be pretty important next week, which is the index shift. All right. And if you are here today and you are here all the way until the end, the index shift part will be two of the questions on your homework that is due on Saturday. Okay. All right. So how do we add or subtract these power series? All right. So let's say that we have one series. We have a sub n, x minus x naught to the n. And it's an infinite series, so we're going to go to infinity. But we're going to say that we just start at some initial point. It doesn't always have to be 0. So when I say n sub 0, I don't mean no. I mean that that is just some random n value that we're going to start with, okay? I don't want to fix a number to it because it could be any number. The point is that whatever number we have here is actually going to need to be exactly the same as the number in the series we are adding or subtracting. So let's say that we are adding or subtracting. We have a second series. It is also an infinite series. And we have n equals n naught, all right? Of another one, so we're going to say a sub n, but let's call it b sub n of x minus x naught to the n. It turns out that, back in the day when you learned about exponent rules, right? Like x squared times x to the third, what does that give us? Yeah, it gives us x to the fifth. And in particular, we added those exponents, right? We x to the fifth. But if we had x squared plus y times y to the third, we wouldn't say xy to the fifth, right? That would be a false statement. And the reason we can't do that is because the bases aren't the same. And so similarly, when we look at adding or subtracting series, we need to make sure that we are starting from the same value. So both of these will be whatever n sub naught is, and we are finishing at the same point, and in this case, infinity. All right, so just like we were really good about checking, are the bases the same when we applied our exponent rules, when we're adding or subtracting series, we want to make sure that that index on the bottom is the same, okay? And so it turns out that if we are adding or subtracting these, we can just say we're going to have n equals n naught, so whatever our starting is, all the way into infinity. And we can just say we're going to do a sub n plus or minus b sub n. So we add those coefficients and then we multiply in the rest of it, x minus x naught to the n, okay? So this a sub n, we saw again over here, the plus minus b sub n and all of that we can sort of group together because they're all going to be coefficients for the same like terms like x minus x naught to the n. Okay, so addition, subtraction, not too bad. Multiplication. So let's see what happens with multiplication. And I'm going to do a lot of writing here. It's okay if you want to just like screenshot this or come back and look at the notes later. But I think one of the trickiest things about sequences and series, and not tricky, but sometimes we just have to write out a lot of terms before we can see a pattern. And I will tell you, I've been in class with some people who don't need to write out any terms at all, and they just get it. And I'm like, oh, okay. I like to write out a lot of terms because when I see those examples, it helps me generalize it more. So it's not something that you should be ashamed of. It's just something that helps you through that process, okay? So let's say we had a series, and let's just say we're starting at 0, right? And we have our a sub n, x minus x naught to the n. So we have our power series, and we're trying to multiply it by this, x minus x naught to the c power, okay? Now I do want to tell you c is a constant, and so c is a fixed number, all right? So our n changes depending on where we are. It could be like 0, 1, 2, 3, 4, but this c is a fixed number. So it could be like 5, it could be 10, but it's going to be a specific number, okay? And so if we were to say, what does this get us? Maybe what we could do is write out the first part and then expand the second part, right? So x minus x naught to the c. And if we write out the expanded form of the power series, not the whole thing, but just a few terms, a sub 0 plus a sub 1x x minus x naught plus a sub 2 x minus x naught squared. Maybe we'll do one more just for good measure, a sub 3 x minus x naught cubed plus, and at some point it's going to be plus a sub n x minus x naught to the n, right? There's going to be an nth term somewhere in there, and then we keep going until we get to infinity. Now, how does that help us? Well, we're going to be really thoughtful about this. And just like when we've seen parentheses or brackets in the past, we're going to go ahead and distribute this to all these terms. Okay, so that x minus x sub 0 to the c power, we're multiplying that in. We're going to distribute that to each of the terms. And then I bet we're going to be able to use some of these exponent properties to help us pack it back up, right? So lots of writing, but we have a sub 0 x minus x naught to the c plus, let's see what happens when I do the second one. I'm going to have a sub 1 x minus x naught. What is the power for this one? Like after I distribute, what is the new power there? Yeah, so let's check this out. I know we did a simpler example here, but both bases were x. And so we were able to say 2 plus 3 gives me 5, right? So when the bases are the same and we're multiplying, we can add our exponents. Well, the same thing is true here. My base is just x minus x naught. And so what am I going to do? I'm going to take this exponent c, and I'm going to add it to this exponent, which is invisibly a 1. So this new exponent will be c plus 1. Okay. Now, next one is a sub 2 x minus x naught. What is the new power for this one as I distribute to the third term?
c plus 2?
You got it, c plus 2. And as I said earlier, I like to write out more because it helps me see a pattern better. A sub 3, x minus x naught to the c plus 3. And maybe at this point, I feel confident enough to generalize the pattern. In other words, how would I write it with n's instead of numbers? And so if we notice, we still have our coefficients, a1, a2, a3, all the way to a sub n. And so when we set up our series to pack it all back up, we can say we're starting at 0, we're ending at infinity. And we know that there's going to be this a sub n in the front because that a sub n will give us all of these a's that we have in the front, all right? But how would I write all of these? Like, how do I know what numbers to plug in? Well, x minus x naught, that part is the same for all of them. Beautiful. And so it turns out that we're just going to take c, and it's a little bit easier to see when we get further down the line, but it's c plus 1, and that's 1. C plus 2, and that's 2. C plus 3, and that's 3. So we can say c plus n. And what we've done is said, if we want to rewrite this, right, we're multiplying in some other powers of x minus x naught, we can actually rewrite that as the following series, right? So we don't have to write out all of the terms in the middle or have sort of two separate ones. We can pack it up into a single sigma notation, okay? So we will use that skill at some point next week as well. All right, so differentiation. It turns out that the power series is a function, right? So the power series is a function, and it is continuous and differentiable, right? Continuous meaning there's no missing pieces. It is differentiable in the sense that it is smooth, and so we can take derivatives of each piece, all right? So because it is continuous and smooth over a given, I'm going to use a keyword here, interval. All right, so over a given interval, it's not true everywhere, but over a given interval, we can say that this power series is a function that is continuous and differentiable. Swallowed the wrong way, sorry. Okay, so if we have this being continuous and differentiable, what it means is that if I have this function, all right, so if I go back to the original power series and I have this function, I can actually do something called term by term differentiation. Okay, so when we're going to do that, we're going to practice this term by term differentiation. All right, so if f of x equals the power series, right? So we have that as our power series. I'm going to say, let's write out a few terms, all right? A sub 0 plus a sub 1, x minus x naught, plus a sub 2x minus x naught squared. Because we're looking for a pattern, I'm going to write one more, a sub 3x minus x naught cubed plus, and it's going to keep going, right? If I think about it in its expanded form, term by term differentiation means if I want to find f prime of x, I can literally take the derivative of each of the terms, and then I can go back and add them together. So let's leave a space for our power series notation. But let's go to these terms that we wrote out, and let's see what the derivatives are, okay? Now keep in mind that any of the a sub n's are a numerical value. And so when I take the derivative of a sub 0, what do I get? We get 0, okay? So this first term is going to go away when I take a derivative. All right, what about the derivative of a sub 1 times x minus x naught? Well, the derivative of that x minus x naught is just going to be 1. And so that leaves our derivative. So let's maybe get 0 plus a sub 1 plus, how would we write the derivative of that a sub 2 term?
2 times a sub 2 times x minus x naught to the first.
Perfect, exactly. All right, and if we do the same thing for the fourth term, we get 3 a sub 3 x minus x naught to the second, right? And we could keep going. We could find every derivative of every term, and then we could add them together, and then we would get our derivative of that power series. And so my question to you is this: how do we write a sigma notation for this series? And maybe we start with this bottom number. The bottom here, I started with n equals 0. What should my new bottom number be for the derivative? Exactly. So n equals 1. I'm still going to go to infinity because I still have all the terms at the end that I got to find the derivative of. All right. A sub n, does that stay as the coefficient, or do I change that coefficient? Well, if we look at what's happening here, it seems like we kept bringing these powers down, right? Yeah, so this was my n, and I brought it down to the front, and I got n times a sub n. In the fourth term, this is my n. I brought it down to the front, and it was 3 a sub 3. And so we can say that our new coefficient is going to be n a sub n, right? A product of those, because we're bringing the coefficient down from the power rule. But if we're using the power rule, my power for this x minus x naught is not going to be n anymore. It's going to be n minus 1. Okay. And so that is how we find our first derivative using term by term differentiation, and then packing it back up into a notation that's a little bit shorter to write. Okay. Now, because we are looking at second order differential equations, it would probably behoove us to write out a pattern for our second derivative if we used term-by-term differentiation, okay? So I'll leave a space here. And let's take our derivative. Derivative of a sub 1 is going to be 0 plus the derivative of 2a sub n x minus x naught. That's just going to be 2a sub 2. All right, what about that third term? If I take that derivative, what am I going to get?
6a sub 3 x minus x naught to the first power.
You got it. So we're going to bring that power down again, right? So we'll have, I'm going to write it as 3 times 2 a sub 3 x minus x naught to the first power. Okay. The only reason I'm writing it as 3 times 2, even though I know that it's 6, I know you know that it's 6, is sometimes when we don't multiply out, it allows us to see that pattern a little bit better. And so if we were to try and write a sigma notation here, it's still infinite. So my top bound is infinity. However, we can see here that the first term went away, the second term went away. So we're now starting at n equals 2. We're not starting at n equals 0 anymore. We're starting at n equals 2. All right. Now, a lot of times, because we typically have the infinity up here, at some point we might not write those infinities, but if you don't see a top bound, it is implied to be infinity, okay? The bottom bound is really where we're going to be spending a lot of our brain power, all right? All right, so what is the pattern that we might see for our coefficient? Well, this looks to be n, right? Because n is 2 here. But then over here, it's like n times n minus 1, right? Because I brought down the next power, the next lower power. And so it turns out that our coefficient is now n minus 1, a sub n, right? So the first n is from this power, and this n minus 1 is from this power, because we're using power rule. And then we have x minus x naught to the n minus lose another power, right? Keep taking that power down as we go. And that is what we know for power rule. Okay. So it's pretty cool. You use this kind of stuff when you're looking at like a lot in partial differential equations. Being able to do term by term differentiation helps out with a lot with something called the Fourier series. Okay. But one thing that we're going to finish off today with is that index on the bottom. Okay, so the number on the bottom is our index. And as we noted from earlier, in order for these properties to be true, the index on the bottom has to be the same, right? So this one was n sub 0, this one was n sub 0. They have to be the same. So we might already see that we have like a 0, a 1, and a 2. And if we're plugging those into a second order differential equation, we might start to run into some problems because 2 is not the same as 1 is not the same as 0. Okay. So this very last skill that we're going to talk about, which again should help you on your, I think, 2 of the questions at the end of, towards the end of your homework, is something called an index shift, okay? The index shift just means change the number on the bottom. Change the starting value or we can think about it whatever that bottom thing is. That's what we're going to be looking at changing. Okay. We need to know how to shift both making that number bigger and making that number smaller, because sometimes it will be easier to bring them all down to 0. Sometimes it will be easier to bring one up to 1 and the other one down to 1. And so to be able to maneuver in both directions would be important. Okay. And so let's take a look at an example. All right, let's say that we have sigma, and we're going to start with an index of 3 to infinity. All right, and we have n squared, a sub n plus 1, and then we have x plus 4 to the n plus 2. All right, so this is our power series centered around x equals -4. All right. And I want us to think about how we can do one of two things, right? So first, we're going to think about shifting from n equals 3 to n equals 0. So we're going to think about how, if we have a number that is higher than 0, how do we get it back down to 0? And then we're going to talk about shifting from n equals 3 to maybe a higher one, like let's say n equals 5. Okay, so we'll practice that shift in both directions. Now, some folks sort of like get the idea pretty quickly. I like to write things out so I'm very clear about how things are moving. And so I typically define a different letter. Okay, you can use whatever letter you want, but I'm going to say I for index. Okay, it is not the imaginary I. So just to be clear about that. If you don't like using I, J is also a common letter to use, and that one gets less confused with the imaginary I because it has a little tail on it. Right. But here's what we're going to do. We're going to start off by saying let, and we're going to define a value for I. I is going to be 3 minus, is going to be n minus 3. Okay. Because if I take 3 and I subtract 3, then I will have a bottom number of 0. Does that make sense? So if I'm thinking about like, how do I get down to the value I want? Well, I take what I start with and I'm going to subtract 3. But I'm wondering, while we're talking about that, what would we let I equal in this second case? Right, if we're starting at 3 and we want to shift up to 5, yeah, exactly. We're going to say to get from 3 to 5, I'm going to take that number, I'm going to add 2. Okay. And so that is how we begin our process. Other than that, if you can add and subtract, you're going to be fine. Okay. All right. So we're really going to replace all of these I's, or all of the N's, with I's. And so it might be interesting to say n equals I plus 3, right? So all I did was take this equation, I added the 3 to the other side, and now I'm ready to sort of substitute, if you will. Okay. So we're going to grab our equation, and we're going to think about what is changing. All right. So in particular, we might notice that if I have n minus 3 down here, this is going to be n equals 0, because I'm subtracting 3 from there. And then everywhere I see an n, I'm going to put I plus 3. So I have I plus 3 squared. A sub, oh, I got an n again. I plus 3 plus 1. X plus 4. Ooh, another n. I plus 3 plus 2. All right, so all I did was substitute everything in. And we're just using this I sort of as like a dummy variable to help us imagine the idea of the shift. And so for our final answer, we do want to go back in and make sure everything is an n. And we want to have everything as an n because we defined like that's what we are counting. Like we're starting at n equals 0 and we're counting accordingly. And so if we shift the index from 3 to 0, our final answer becomes n plus 3 squared, a sub n plus 4, x plus 4, n to the 5th. All right, and so all I did here was go ahead and add all the numbers, right? So everything like this 3 plus 1, this 3 plus 2, that's how I got the 5, and that's how I got the 4, right? And so this, my friends, is how we perform an index shift, all right? So we're changing the equation to say, I've got a different starting point now. Help me accommodate that in my power series representation. All right, so let's do one more here. All right, so we're going to shift from 3 up to 5. And like Elliot said, we can let I equal n plus 2. All right, that means that n could be I minus 2. And now I can go ahead and substitute. And so we are shifting now to 5. And so everywhere I see the n, I'm going to put I minus 2. So I minus 2 squared, a sub I minus 2 plus 1, x plus 4 to the I minus 2 plus 2. And if we clean that up, we get n equals 5 to infinity, n minus 2 squared. A sub, let's see, negative 1 plus 2 is n minus 1, x plus 4 to the n. And so when we shift up, we notice that we sort of don't have that plus 2 anymore because we moved everything up by 2. And that meant that our a sub n plus 1 moved backwards to an a sub n minus 1, and that this n squared became n minus 2 squared. Right? So I think one thing that would be valuable to kind of practice over the weekend is this idea right here. How do you set up that index shift? How do you substitute it in there? Because again, we'll be using this particular skill a lot next week. All right. So folks, that is all we have for today. I wasn't sure how long that was going to take, but I think we're good timing.